Here in our universe, despite how vast it is and how intricately we can probe it, there are still limits to what we can observe, test, and measure. We can obtain signals from very far away and infer the existence of an early, hot, dense, uniform, and rapidly expanding state. The hot Big Bang. However, even the earliest signals that we can detect don't take us all the way back to the start of the Big Bang itself, just as close to it as we can get. It's up to us to infer the rest. Similarly, we can only detect signals from outside of a black hole's event horizon, both before and after the formation of a black hole. And yet, from the properties that we do observe, we can conclude that black holes exist, including their locations and masses, despite not being able to probe the interior of the black hole itself. The idea that black holes exist has been around for longer than most people realize, since the late 18th century, when John Michell first suggested them. He noted that if you took something like our Sun, with a known mass and volume, and simply created a bigger version of it, with more mass occupying more volume at the same density, you'd eventually reach a critical situation. At some point, with more mass gathered together in one region of space, you'd find that the escape velocity from the surface, or the speed at which you needed to move to escape from the object's gravitational pull, would exceed the speed of light, which is 300,000 kilometers per second. From outside of this object, you wouldn't be able to see anything at all, as not only could light not escape from it, but no particles or signals of any type. Anything that happens within the interior of that surface, where the escape velocity is greater than or equal to the speed of light, can never get out. With that, the idea of a black hole was born. And a little over 100 years later, when Einstein came up with the general theory of relativity as our new theory of gravitation, the idea of a black hole became even more compelling and robust. But what exactly happens at the edge of a black hole? According to Einstein, it isn't that objects have mass and massive objects attract one another through an invisible force. That conception of gravity is Newtonian and cannot explain a whole host of observational phenomena, from the gravitational bending of light to the orbit of Mercury, to the presence of gravitational waves, and much more. Instead, Einstein's revolutionary new way to view the universe asserted that matter and energy alter the curvature of spacetime and affect its evolution, and that this curved and evolving spacetime tells matter and energy how to move within it. If you have a point-like mass in your universe, that creates the Schwarzschild spacetime, the spacetime that describes a non-rotating black hole. Any massive particle that you place down in that spacetime will experience the spacetime curvature induced by that black hole. Imagine for a moment a particle hovering near the edge of a black hole. If that particle is outside the black hole's event horizon, then it could still escape from the black hole's gravitational pull if it were moving fast enough. The event horizon acts as a boundary. The rules of physics as we know them cease to apply. However, if that particle were placed inside the black hole's event horizon, then it could never escape. It is doomed to spiral inexorably towards the central point, the singularity, after a finite and calculable amount of time. At the singularity, the curvature of space-time becomes infinite. What was remarkable about black holes in general relativity is how easy they were to produce theoretically, as well as how difficult they were to avoid. One of the earliest results that Einstein was able to show is illustrated here. Imagine a flat, static, unchanging spacetime. Within this spacetime, you place a set of stationary, pressureless masses, often referred to as dust particles. These particles, once set in this environment, begin to interact under the influence of gravity. As these masses evolve, they gravitate towards each other, inevitably leading to the formation of a non-rotating black hole, complete with an event horizon. But now we're moving on to an even bigger question. What about the entire universe becoming a black hole? If the universe were initially static, as describable by a non-evolving spacetime, then filling the universe with large amounts of matter, radiation, or energy of any form would lead to it quickly collapsing. Energy causes space to curve and evolve doesn't just mean to distort a fabric with peaks and valleys in it, but also includes allowing that space to either expand or contract. The universe could potentially collapse into a gargantuan black hole, an all-consuming singularity where the laws of physics as we know them cease to apply. One of the most remarkable and perhaps underappreciated aspects of Einstein's equations is also a feature of many other equations in physics. They often have multiple solutions to them. When you throw a ball up into the air, you can write down equations that tell you when it will come down and hit the ground. And if you solve those equations, you'll find something that you perhaps didn't expect. You'll get two answers. One of those answers will correspond to the physical scenario you're interested in when the ball hits the ground after you've thrown it up into the air. The second of those answers, however, will correspond to an unphysical scenario, the one where the ball would have started off on the ground prior to being thrown, assuming it was moving even faster than before you threw it. Similarly, if you take a universe and fill it uniformly with any species of energy that you like, normal matter, dust, dark matter radiation, neutrinos, or dark energy, a cosmological constant or field energy during inflation, you'll find that there are two valid solutions within Einstein's equations that emerge. One solution corresponds to an expanding universe, where the distance between any 2 points increases with time. The other solution, however, corresponds to a contracting universe, where the distance between any 2 points decreases with time. At this point, our universe is indeed expanding. That's the situation that corresponds to our physical reality. Moreover, measurements of the expansion rate across cosmic history, which can tell us how the expansion rate has changed over time, show a tremendous consistency with the solution of Einstein's equations that correspond to an expanding universe. Today, our universe is composed of 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos, around 0.01% photons, and a negligible amount of everything else. In the past, the universe was expanding more rapidly, and as time continues forward, the expansion rate continues to decrease, where it will eventually approach about 80 to 85% of its present value. If we go back in time, however, either to the early initial state of the hot Big Bang, where all of the energy was in the form of particles and antiparticles, or even earlier to the preceding period of cosmic inflation, where all of the energy was in the form of energy inherent to space itself, example, the field energy of inflating space, we still can't get rid of that initial expansion. It must have also been present even all the way back some 13.8 billion years ago. That's where the key to the answer lies. The universe is expanding today. The expansion rate is decreasing with time, and hence in the past the universe must have been hotter, denser, smaller, and more uniform. What's also true, although we don't often emphasize it, is that the expansion rate must have been much larger in the distant past as well, closer to the Big Bang as well as before, during the period of cosmic inflation that preceded it. If we didn't have this physical information about the universe, we wouldn't have enough information from theory alone to answer the question. Instead, there would have been several possibilities for how the matter and energy in the universe related to the curvature and evolution of spacetime. The universe could have begun by contracting, and the matter energy within it would have led it to collapse, either to a big crunch or into a black hole. The universe could have begun stationary and static, and the matter energy within it would have led it to collapse, either to a big crunch or into a black hole. Or the universe could have begun by expanding, and the matter energy within it could lead to a recollapse, an eternal expansion, or the critical case, where the expansion and the matter energy contents of the universe were perfectly balanced. This is what we call a fine-tuning problem in physics, where it seems like all of the possible outcomes were equally likely, but somehow, the universe arrived at a very unlikely outcome. It was by searching for and finding a mechanism that could explain why these two properties were balanced. An early phase of energy inherent to space dominating the expansion, also called inflation, that led to the revelation of what precisely happened before the Big Bang occurred. Even though we recognize that matter and energy curve space, and that curved space then tells matter how to move, we often omit an important aspect of how space curves in our head. It can curve by expanding or contracting as well. It's only because the universe that we know began by expanding, and expanding not only rapidly, but in practically perfect balance with the matter and energy density that was present at every moment, that the universe didn't collapse in on itself almost immediately after its beginning. The expansion must have happened at the start of the hot Big Bang, and even before, during cosmic inflation. If it weren't for this property, this initial condition of the universe, then collapse would have been inevitable. But who or what set these values for the universe? And why do the universe seem so perfectly suited for that can harbor life? Some theories suggest the existence of a multiverse, where countless universes each have different physical laws and constants. We find ourselves in one of the rare universes where the conditions are just right for life. Others propose that these constants are the result of deeper, underlying principles that we have yet to uncover. This is end of our exploration. Hope you enjoyed it. Thank you for coming this far with us.